Hello, everyone. Welcome to the plenary session. I'm Richard Shane, a Vice President of the AMS, and it's a pleasure and honor to introduce our next speaker, André Neves from the University of Chicago. It's also a personal honor to introduce André since he is a former PhD student of mine. Over the last decade, André has done some of the most important work in differential geometry. This includes the resolution of the Wilmore conjecture almost 6 years ago, as well as recent spectacular work on the variational theory of minimal hypersurfaces. André has received lots of recognition for his work, including the 2016 Veblen Prize awarded by the American Mathematical Society and the 2015 New Horizons Prize in Mathematics. The plateau problem was posed in 1760, but was not solved mathematically until the 20th century. It is the construction of a surface of least area spanning a closed curve in space. The solution surface is called a minimal surface. Since such surfaces are so hard to construct, we who think about such problems we consider them to be very rare and special. So it came as a real surprise when André and his co-workers recently showed that such surfaces exist in sufficient abundance to uniformly fill the space in which they live. He's going to tell us this story in the talk today, so please join me in welcoming André Neves.
Okay. So I want to thank Rick for the kind words. You know, it was a pleasure to have him as an advisor. He was like the inspiration for all this work. So I'll talk about some ongoing work that I've been doing with Fernando Marques, and over the last 6 months that had a big improvement with some joint work with Kairi and Antoine Song. So let's talk with so I'll start with a foundational question in geometry, but also in mathematics. So this was a question posed by Poincaré in 1905, and the question that Poincaré posed was whether you can always find a closed geodesic on any given two-sphere. So the reason why this question turned out to be foundational in mathematics, it's because geodesics, they have two distinct points of view. On one hand, we can see them from the variational point of view, and so the definition is that closed geodesics, they are critical points for the length functional, and they have the property that given any two nearby close points in the curve in between them is the shortest path connecting these 2 points. And so the question that Poincaré is asking is, can we always find closed geodesics even when minimization does not work? Because the easiest way to find a closed geodesic, because it's the critical point for the energy, for the length functional or the energy functional, it would be to find a curve on your surface which is not homotopically trivial, and then you minimize the length in that homotopy class. Of course, on the two-sphere, it happens that every curve you pick, if you minimize length in that homotopy class, you're going to get 0 because you can shrink the curve to a point. And so you will find, so for instance, in this bean I drew here, which is a topological two-sphere, you have a geodesic there, but the geodesic is not length minimizing, so I can surely push it inward and will minimize the length. So the other point of view for geodesics is that the geodesic flow is Hamiltonian, can be seen as a Hamiltonian flow on the cotangent bundle. And so another way to try to produce geodesics would be to just pick a point on the manifold, pick a direction, and then just shoot a geodesic starting at that point with that given direction that will go round and round on the two-sphere. And then you hope that eventually this orbit will close. And so the question becomes, do Hamiltonian flows in general have periodic orbits? Okay. And around 7 years after the question was posed, Birkhoff, he showed that indeed on every two-sphere, one can always find a closed geodesic. And 20 years later, so I'll say some words about the method soon. So 20 years later, then Luschenich and Schnirelmann, they showed that actually you can always find 3 simple closed geodesics on any 2 spheres. So simple means they will have no self-intersections. Okay, so let me make some comments about both proofs there. Okay. So the first comment is that both proofs use the variational point of view of geodesics. So the way they work is so they realize that they show that the space of simple closed curves on the 2 sphere has sufficient topology, and then they realize that if some space has some topology, then that should force the functional, which in the case is a length functional, to have critical points. So Birkhoff and also Luschenich-Schnirelmann proof, in some sense, they were ahead of their time because they were reasoning like what became later known as Morse theory, but doing this pre-Morse theory. So Birkhoff proof, the way he proves the existence of the closed geodesic is using what's now known as the min-max method, and that was the first application of min-max methods in geometry. So then the final comment about the proofs is that in some sense, this Luschenich-Schnirelmann theorem was so ahead of their time that a full complete proof only was done in '89 because the subtle statement is to make sure that the closed geodesics you find, that they are simple. So Grayson, he did this in '89 using the curve shortening flow. Okay. So the second comment, and I guess that points to the beauty of the Luschenich-Schnirelmann theorem, is that the result is optimal on some ellipsoids. So one can find some ellipsoids where there are only 3 simple closed geodesics. So, and these are the intersection of the ellipsoid with the coordinate plane. So if I intersect with the z-x plane, I get this red geodesic. If I do intersect with the xy plane, I get the blue geodesic. And if I intersect with the zy plane, I get like this geodesic there, which will be a black curve. Right? That does not mean that there will be no other geodesics on the ellipsoids. And actually, I showed you a picture of another ellipsoid where besides having these 3 simple closed geodesics, it has another geodesic which has lots of self-intersections. So the statement, the optimality is that there are ellipsoids in which you can find only 3 simple closed geodesics. You're going to have a lot more geodesics, but they will not be simple. They're going to have lots of self-intersections. Okay. So since this seminal work, there was a lot of activity in the problem of finding closed geodesics. And so I'm just choosing some of the highlights. And so there's a famous result of Bowen in '73, where assuming that the ambient curvature of the closed ambient manifold is negative, then they show that closed geodesics of large length become equidistributed. What this means is that you pick some open set in your manifold, and then you take some geodesic of very, very large length. You look at the ratio of the length of the intersection of the geodesic with the open set. You divide by the length of the geodesic, and that should approximate the ratio between the volume of your open set and the volume of the total manifold. Okay. So, an interesting comment is that is regarding this curvature assumption. So, for the purpose of existence theory of closed geodesics, the general trend is that when you have negative curvature, if you work on a closed manifold, your fundamental group is very rich, and so you have lots of topology, and so you have lots and lots of geodesics. So geodesics tend to exist in great quantities for negative curvature, if it's negative, and to be scarcer if you have positive curvature, like the sphere. So for the purpose of existence of geodesics, the one that should have the least, the manifold that should have the least ones should be the sphere somehow. Okay. And so Pugh and Robinson, in '83, they showed that for a C2 generic set of metrics on any given surface, regardless whether you can put a metric of negative curvature or not. So for instance, here the sphere or the torus qualifies. The sphere and the torus does not qualify in that theorem. So they show that for a generic set of metrics, then the set of closed geodesics is dense, meaning you pick some open set, and then for sure you're going to find some geodesic that passes through that dense set. So 3 years ago, Irie, one of our co-authors, actually improved from C2 genericity to C infinity genericity, and he did this using embedded contact homology, more precisely a Weil form, a Weil law that was proven in the context of embedded contact homology. And the important comment about both proofs is that they use the dynamical point of view of geodesics, seeing as periodic orbits of some Hamiltonian flow. In the case where the ambient curvature is negative, then the geodesic flow gets a special structure. So that's why the results are much stronger. Then to end the case of the geodesics, then there's a famous result of Franks and Bangert from 1992 and 93, respectively. And the result is that on any two-sphere, you can always find infinitely many closed geodesics. So the previous result here is the C2 generic condition, and so this condition is removed for the two-sphere. And if the ambient manifold had been any other surface, one already knew that you could always find an infinite number of closed geodesics, regardless whether the metric is generic or not. So the hardest case is always the two-sphere. Interestingly enough, for this theorem, both perspectives are used. Franks uses the dynamical point of view perspective, and Bangert works using the variational perspective, and the results are somewhat complementary, meaning when one perspective does not give infinitely many closed geodesics, then the other one covers the remaining cases. Okay. So this was just a very short overview of the geodesics case, and now I'll move on into the minimal surface. Okay. So in the same way that geodesics are critical points for the length or energy functional, minimal hypersurface, they are critical points for the area functional. So the problem that Rick mentioned, the plateau problem, is you pick some curve, you look for the surface of least area whose boundary is the boundary of that curve, and because you obtain the surface of least area, that will be a critical point, and thus will be a minimal surface. Okay. So as Rick mentioned, they are, even on R3, they are not so easy to find. So the first 3 examples of minimal surface, they were found in the 18th century. So the first example is just a plane in R3. The second example, they were found by Euler and Mesnier around the same time, and this would be the catenoid, and the other one would be the helicoid. Then, in the 19th century, mathematicians were able to find other minimal surface, but they were all double periodic or triple periodic or singly periodic. So this one is called the Scherk minimal surface and is singly periodic, right? You have this pattern that just repeats all over. But if one asks about minimal surface of finite topology, then the only known examples beside the plane, they were the catenoid and the helicoid, because this one would have infinite topology, so we are crossing it out. And so there was like a period of 200 years where the only minimal surface mathematicians knew of finite topology, they would be the plane, the catenoid, and the helicoid, until Costa, I think in the 80s, found this genus 1 complete embedded minimal surface. And then since then, we have found a lot more minimal surface in R3 using several different methods. And there's a good understanding of what minimal surface in R3 now look like. So these minimal surface, they are taken from the webpage of Matthias Weber. So he runs what would be like the national art gallery for minimal surface in his website. And if you see it there, he has a little history about all the classical minimal surface. Okay, it's in his website. And I also want to point out that minimal surface, they are ubiquitous in science, and they appear from general relativity, where they are called apparent horizons, but also in more applied fields like material science or biomedicine. So this minimal surface we see here, that's a triply periodic minimal surface called the Schwarz p-minimal surface, and was found in the 19th century. And this one is also a triply periodic minimal surface, is called the gyrod, was found by Alan Shane in the 70s. You know, in this picture, this is a block copolymer which has a highly porous structure. So you and his team, what they did was they used some scanning electron microscope, and they were able to construct some copolymers with a very high porous structure, where the pores are exactly like the Schwarz p-minimal surface or like the gyrod minimal surface. They are interested in doing that because, as they explain in the paper, for pharmaceutical purpose, this porous structure is important to be able to transport the drugs easily. And here, this was a paper from some chemists where they construct copper having, again, this highly porous structure which mimics the Schwarz p-minimal surface. Okay, so these minimal surface, they are highly stable structures which are found in several natural problems. Okay? So now, going back to the realm of geometry, pure math, so Lawson, in the 70s, he showed that if one looks at the round tree sphere, then we can find a minimal surface of an embedded minimal surface of every possible genus. So this result is interesting because I guess that at the time that it was shown, this became the first example of having minimal surface, a finite topology in the tree sphere, because, as I said, the tree sphere should be the case, or the topological tree sphere should be the case where it's hardest to find minimal surface. And so Yao, I think motivated by Lawson result, but also by the development, by what was happening in the case of geodesics, Yao he conjectured in 1982 that on every closed tree manifold, one should be able to find an infinite number of distinct minimal surface. And so I guess if you want to understand this conjecture or make some progress on it, the first thing you have to wonder is if you can at least find one. And this was done around the same time. So this was done by Pitts and also by Shane Simon. And the result is that given any closed Riemannian manifold, then you can always find one closed minimal embedded hypersurface, which will be smooth outside a set of codimension 7. So this existence of a possible singular set is a condition that has to be there, and it's well understood in the theory. So the result is optimal. Okay? And the way this theorem is proven, it's similar to the way that Birkhoff found a closed geodesic on any given two spheres, so follows the same methodology. Okay? So Pitts and his advisor Almgren, they did what now we call the Almgren-Pitts min-max theory, and so they produced the competitor, or they produced the candidate to be the nice, smooth, embedded minimal hypersurface, and then Shane Simon did the regularity part, meaning showing that that competitor is actually the smooth and embedded outside a set of codimension 7. Then around this time, there were a lot of developments of minimal surface theory with many famous problems being solved, namely the positive mass theorem of Shane Yao, for instance. But on the subject of trying to find more minimal hypersurface on a given closed manifold, the subject was pretty much stopped. This was the best result for more than 30 years. And then 3 years ago, with Fernando Marques, we improved this Pitts-Shane-Simon result, and we showed that given any closed n+1 dimensional manifold, we can always find n+1 minimal embedded hypersurface, which will be smooth outside a set of codimension 7. When the ambient dimension is between 3 and 7, and assuming a curvature condition, assuming that we have positive Ricci, then we show that in this case, one can indeed find infinitely many closed minimal smooth embedded hypersurface, which means that Yau's conjecture becomes true then for metrics with positive Ricci curvature. So let me make some comments about the dimension here. The correspondent result, if we require n to be 1, meaning the ambient dimension to be 2, it's not true, because as I showed you on the second slide, there are ellipsoids in which you have only 3 simple closed geodesics. Every other geodesic will not be embedded, will have lots of self-intersections. While in the result here, one assures that these minimal hypersurfaces are embedded. They will not have self-intersections. Okay? Then the second comment was that usually, as I said, spheres are always the hardest case to find minimal embedded hypersurface. And so when we proved this result, both Fernando and I, we felt that we were somehow on the right track. Okay? And then Shinzu, 2 years later, he removed the dimension restriction, meaning just assuming the ambient manifold as dimension 3 or higher. And he showed that on any manifold of dimension 3 or higher, if you have positive Ricci, then you can always find infinitely many closed minimal embedded hypersurface, which will be smooth outside a set of codimension 7. Okay. So now, recently, there has been some progress in the question of finding minimal hypersurface. And so some month ago, with Fernando Marques and Kei Erie, we showed the following result. So the setup is, let's take an ambient manifold whose dimension is between 3 and 7. And then what we showed is that for a generic set in C infinity, for a generic set of metrics, the set of all closed minimal embedded hypersurface are dense. What this means that if you pick an open set U for a generic set of metrics, you'll always have a minimal surface passing through that set U. Okay. In particular, this result implies that Yau's conjecture holds true for generic metrics and actually without the dimension restriction. Then 1 month later, again with Fernando and with Antoine Song, which is a student of Fernando Marques, we showed that for a C infinity generic set of metrics, we can find a sequence of closed minimal embedded hypersurface that they become equidistributed. So what this means is that if we pick an ambient function, and if we average, if we integrate the ambient function all over, say, the first K, Q minimal surface, and we divide by the total volume, as Q goes to infinity, we recover the average of the function on the ambient manifold. So this result is giving a quantitative description of the denseness result. Okay. So so let's make some comments about the proof. And I guess the first comment is that the similar results for geodesics. So this one, the analog would be the Pugh-Robinson result. The analog of this would be the, I forgot the name, I apologize, equidistribution, the equidistribution result. Both theorems, they use, the proof relies on the dynamical point of view for geodesics. In our case, in the case of minimal high hypersurfaces, dynamical point of view does not seem to have an analog, and so the only tools one has, they are variational. in nature. The major difficulty in using the variational tools is that it's hard to distinguish between the critical points. And what I mean is the following. So given a minimal surface, which is a critical point for the area functional, then it's a valid critical point to take this minimal surface and just multiply by 3. So because you can see this minimal surface as a measure, and then in that case, this would just be the same measure multiplied by 3. From the variational point of view, both are minimal surface. On the other hand, geometrically, they should not count as distinct ones because it's just the same thing with some multiplicity. So the easiest way to see this is in the case of geodesics, right? In the case of geodesics, we can have a geodesic which is a critical point, and then we can consider the same geodesic just going around 3 times. This would be like 3 times the geodesic. This would count as a different critical point when in reality the geodesic is the same. Okay? So the fact of the existence theory not rule out, not distinguish between a minimal surface and its multiples, it means that the variational theory can give you lots of critical points, which could end up being always the same geometric eye with different multiplicity. Okay, so this is the undercar, the underlying difficulty for the problem. So each time one makes significant progress on a question that has been open for a while, usually it means that we have to bring some ideas which are out of the box. In our case, the new ingredient we bring is this Lie law for the volume spectrum, which I'm going to explain now. Okay. So we have to change gears slightly now, and let me just recap what is the standard spectrum for the energy. Okay. So let's just consider some closed Riemannian manifold, and there's a natural space of functions there, which is the W12, and so this is the space of functions which have bounded energy and bounded L2 norm. Okay. Now, this is a Hilbert space. You can think of it as being R infinity, if it makes any sense. And so on this space, we remove the origin, and we consider an equivalence class. And the equivalence class is such that we identify the function with all its multiples. And we mod out the space by this equivalence class, and we get a new space, which I'm denoting here by curl P. Okay? So let's suppose for a moment that W12 was just a finite dimensional vector space. So if you have a finite dimensional vector space, if you remove the origin, and if you identify 2 vectors to be the same, if they have the same direction, then what you get will be a projective space. Okay? So here we are doing the same thing, but instead of being a finite dimensional vector space, it's an infinite dimensional one. But when you do the equivalence class, you're not going to get a projective space. You're going to get something which will be the infinite dimensional projective space, RP infinity. Okay? And to stress this idea once more now, if we take a P+1 dimensional plane in W12, when we do this equivalence class, then this P+1 dimensional plane in the space P becomes a P-dimensional projective space. Okay. And the Pth eigenvalue is given by this formula coming from the Rayleigh quotient, which is the following. So we fix some integer P, and we do the following min-max. We choose one of these P projective spaces that lies inside P. And on this projective space, we maximize the Rayleigh quotient, the quotient between the energy and the L2 norm. And then we minimize among every possible projective space. There's a comment one needs to make here is that an element on this P projective space is not a function. It's an equivalence class of functions. So when we pick an equivalence class, we have to choose a representative. But the good thing is, when we do this quotient, it doesn't matter which representative we chose, because if instead of f, we just take some other multiple, the quotient will be the same. This is scale invariant. Okay? So this Rayleigh quotient is well defined in this space of equivalence classes. Okay. So this is an alternative way of saying what the pth eigenvalue for the energy is. And when one learns the spectrum of a manifold, usually one of the first results we see the proof of is what's known as the Weil law. So this was proven by Weil in 1911 and by Meenakshi, Shadram, and Playel in 1949. So the result is that if we divide, so this pth eigenvalue, as p goes to infinity, they are going to infinity. The result is that if we divide them by their growth power, then we're going to get a limit which is just a universal constant times the volume of the ambient manifold. So the asymptotic limit of the eigenvalues only depends on the volume of the manifold. And because one can compute this spectrum on specific examples, so we can compute this either on a sphere or on a torus, then we can know exactly what the value of this constant is. For the record, just 4 pi squared times the volume of the unit ball with the appropriate power. Okay. An important, so this result, this had been was first observed experimentally by Lord Rayleigh in the 19th century in a book he wrote called The Theory of Sound, where he verified, so he checked the frequencies for different instruments with the same volume, and he was able to see that as the frequencies get very large, their limit will only depend on the volume of the instrument and not on the precise shape. So the first frequencies, of course, depend on the precise shape of the instrument, but not the bigger ones. They just take information on the volume. And that became a conjecture. Weil was a student at the time. He learned about this conjecture, and the legend says that he proved shortly after. So Weil's proof is variational. In the point of view is variational. Then Weil's proof is variational, but it only applies to domains in space. It does not apply to a manifold with no boundary. Okay? The proof for the boundaryless case, for the case of closed manifolds, only came many years later by Meenakshi, Chandram, and Playel, where they used the trace for the heat kernel. So they used a different method, which is not variational in nature. So now I'm going to redo this set of ideas, but instead of applying them to the space of W12 functions with the Rayleigh quotient, I'm going to apply them to the space of mod 2 cycles with the volume functional. Okay, so let me explain that. So now the space we are interested is the space, so this is known as the mod 2 cycles, mod 2 codimension 1 mod 2 cycles, and you can see them as just all possible boundaries of every region in space M. So this is the space of codimension 1 mod 2 cycles, which are in the connected component of 0. Okay? Almgren, so this space, there's a suitable topology there called flat topology, and these spaces are well studied in the field of geometric measure theory. So Almgren, he showed in 1961 that this space, this was his thesis, he showed that the space is weakly homotopic to RP infinity, in the same way that the space of W12 minus the origin with that equivalence class is weakly homotopic to RP infinity. So if this space has the same homotopy type as RP infinity, then the cohomology ring has to be the same, and so there's only one generator, which its cup powers will generate the whole cohomology ring. And of course, we have coefficients in Z2. Okay. So now, so we have the space. We want to have a suitable notion of what should be a p-projective space, right? And so one notion proposed by Gromov was the following. So we take X to be just some finite dimensional complex, and we consider a map from this finite dimensional complex into this large space. And then we say the map is a p sweep out, if when we pull back this generator in singular cohomology and we take its p power, then we get a non-trivial element in the pth cohomology with Z2 coefficients of X. So the name p sweepout is well given because what this means is the following, that so X is a parameter space. And what this means is that, roughly it means that if we choose p points on the ambient manifold M, we can find a point X such that the image for phi under this point X, which will be a hypersurface, passes through these p points. So that's why it's called a p sweepout. Okay. And so now the p sweepouts, they are playing the role of a p projective space. And so reasoning with analogy, by analogy with the Weyl spectrum, Gromov, he introduced the volume spectrum, which we define the following way. So this is the omega PM, we call this the p width. So we look at a p sweepout, and then we maximize. So a p sweepout is just some, you can imagine as a p parameter family of hypersurface sweeping out your space. And so you take one such p parameter family, and you maximize the volume of this hypersurface, and then you minimize among every possible p sweepout. So formally, this is exactly like the pth eigenvalue, right? The pth eigenvalue is we take a p projective space, here we take a p sweepout, and then for the pth eigenvalue, we maximize the energy, the Rayleigh quotient. Here we maximize the volume, and then we minimize among every p projective space, and here we minimize among every p sweepout. But formally, the idea is the same. Okay. And so Gromov, he introduced this, and he conjectured that this spectrum, which is a nonlinear spectrum, should also obey a Weyl law. Meaning, if we divide the p width, omega pm, by p to the n plus 1 root, then we're going to get a universal number times the volume to the appropriate power, because this is how the problem scales. So Gromov and Larry Guth, they show that the n plus 1 root of p is the appropriate growth for the pth eigenvalue. Okay. So this volume spectrum, this fits in a larger narrative of Gromov in this concept of nonlinear spectrums, where he defines spectrums for every space which is weakly homotopic to Rp infinity, and for a very large class of functionals. And Gromov's point of view is that many of the properties that we observe and prove for the energy spectrum, they will also have some translation in the nonlinear case. Okay. So now I will talk about the two main ingredients that Fernando and I and our co-authors use to prove the denseness and the equidistribution. So the first new ingredient is this theorem from 2 years ago, due to Lukumovich, Fernando, and ourselves. And what we show is that Gromov's Weyl law holds, meaning indeed, regardless whether the manifold has boundary or not. So what we showed that indeed there's a universal constant such that if you divide the p width by the growth power, then you get this universal constant times the volume. So we were able to prove this Weyl law without knowing the value of alpha n. This is in stark contrast with the Weyl proof for the Weyl law, because the way Weyl proof works is first you compute the spectrum of cubes, and then you compare every region of the, oops, let me see. I'm going to try to press OK and see if something happens. OK, should be fine. So in Weyl's proof, you compute the spectrum for cubes, and then you compare every region in the domain with a bunch of cubes, and use the fact that you can compute it explicitly for cubes to deduce the Weyl law for other regions. Okay. In our case, we follow the same approach for domains in space, but we have to get along without knowing how to compute on a single example. Interestingly, when the manifold is closed, while proof does not apply, because when the manifold is closed, the way you prove the while law is using this trace for the hit kernel, which in the case of this volume spectrum, we wouldn't even know where to start. There's not even a hit kernel to start with. And so to prove for the closed case, we take advantage of the fact that we work in the volume functional. We can use a lot of cut and paste arguments, and so we argue more in the spirit of geometric measure theory. So the second new ingredient, so this is the min-max theorem. So let me just say it and then explain what's the novelty about it. So this is due to Pete, Shane, Simon, but in the version I'm going to write here, there was also a contribution that Fernando and I did. So I'll state the theorem. The theorem is that if you take an ambient manifold whose dimension is between 3 and 7, and the theorem is still valid without this restriction, but let's just do this for simplicity. Then the theorem says that for every integer p, you can find a closed embedded minimal hypersurface with possible multiplicities that realizes this p width. Okay? So this result is important because it's what making the connection between minimal surface and the volume spectrum. Okay? And again, I stress out that these minimal hypersurface, they can be, for instance, two disconnected components where one has multiplicity 2 and the other one has multiplicity 3. And it's the presence of these multiplicities which makes both the denseness and the distribution and just the existence in general to be a subtle issue for minimal hypersurface. So this result had been proven by Pitts and Shane Simon in the context of min-max in a given homotopy class. The difference is that this volume spectrum is not done over homotopy classes, is done in cohomology classes. And so to be able to use the theory that was done in homotopy classes, to be able to extend that for cohomology, one needs to have some uniform Morse index bounds on the min-max minimal hypersurface, and this is what Fernando and I did. So Fernando and I, we proved that this minimal hypersurface, its Morse index will be bounded by p, and using that, one can just pick the theory that was done for homotopy, and that will carry over in this setting. Okay. So now in the, in the 7 minutes I have left, I will describe, roughly speaking, how does the while law help you to prove the denseness and the equidistribution. Okay. Okay. So the first result is that for a generic set of metrics, minimal hypersurface is dense. So the basic strategy is the following. Given a metric G, I have to put here some notation. We let curl M of G to be the set of all minimal embedded hypersurface with respect to that metric G. So as far as we know, this set could only have n plus 1 elements. Okay? And now we choose an open set U, and we look at the set of all metrics for which you can find a non-degenerate minimal surface that passes through the set U. So the condition non-degenerate, it's like saying that the volume functional is a Morse functional, is the same thing as saying that the volume functional is Morse with respect to this metric G. Okay. So because we have this non-degeneracy condition, one can show that this set is open. If we can also show that the set is dense, then we let U to be a countable basis of open sets. We intersect a countable number of open dense sets, and we get a generic set. And this is the set of metrics for which minimal hypersurface will be dense. And so very broadly, the way the proof works is by contradiction. We suppose that's not the case, that the set is not dense. And so what this means is that I can find an open set of metrics where no minimal hypersurface goes through a fixed set U in the manifold. And doing that, and then just by changing the metric on that open set U, we construct a path of metrics in that open set, which has a property that the minimal surface with respect to this path of metrics is not changing. So the set of minimal surface will remain the same, just the metric is changing. we are able to construct that, of course. And moreover, more importantly, this volume spectrum does not change with T, remains constant. Okay? But of course, the metric is constructed just by a compact perturbation on U, and so I can put that in a way that the volume at the final time is bigger than the volume at the initial time. And then from Y law, I know that asymptotically, this pith width, or asymptotically this volume spectrum, tends to the volume if I divide by the appropriate rate. So there's no way that the volume volume spectrum can be constant as a function of T, and that's where the contradiction comes from. Okay? So let me now explain what's the key to get the equidistribution. Okay? So the equidistribution result is a bit more subtle. So I'll just explain one key step. So let's fix a metric G. So I want to find a sequence of minimal hypersurface that becomes equidistributed. So let's fix a metric G. And then let's pick K functions on K smooth functions. And I want to find a tiny perturbation of this metric G, which I call G bar, which has the property that if I average any of these K functions over my minimal surface, I get very close to the average of these K functions over the ambient manifold. And then, of course, I let K go to infinity. So I want to show that the set of such guys is open and dense. And then, of course, I take the intersection of all such guys, and I get my generic set. Okay? So let me explain how to find this. So take these K functions, and let's see them as a vector. And now I'm going to consider a function defined on a tiny K-dimensional cube, which is given in the following way. So let's take a point in the tiny cube. So this is a K vector in this K-dimensional cube. And from this K vector, I consider the following tiny perturbation of the metric G. I just do a conformal perturbation, which I do 1, plus I do the dot product between this vector and this vector of functions. So this gives me a conformal deformation of this ambient metric G. Okay? And then I consider the following function. For each P fixed, I take T inside the cube, and I do the logarithm of the P width for this metric. I subtract this n over n plus 1 times the logarithm of the volume for this metric, and I also subtract this constant. Okay? This function makes sense to choose for two reasons. The first one is that, so this is a function from a cube into R. Its gradient, it's K vector. It's a vector from a cube into RK. If I look at the components of the gradient, I get exactly this thing that I want to choose is small, that I want to prove it's small. So this is the gradient of this function. So that itself is a good reason to pick this function. Moreover, what the Y law says is that as P goes to infinity, this function is going to 0 uniformly. Okay? So now I have a function who's going to 0 as P goes to infinity, assuming I can differentiate with no problem, then I should have a point for each P. I should have a point where the derivative is small, and so if the derivative is small, I find the minimal hypersurface where this guy is small. The difficulty in making this into a rigorous argument is that the function is not smooth. In general, it's only Lipschitz. And so it could be that the function, it could be that the gradient is always big. Okay. Okay. So I'll just stop here. Let's see. Did I stop? Yeah, right on time. And I want to thank you for your attention.
Hi. I just have a question on 3 slides back. So you...
Wait.
Yeah, 3 slides back where you're proving the dense theorem.
Two?
Yeah, here.
Oh, okay,
The
wait.
dense theorem proof. So
Got it.
before you've got to this point, you might have the minimal surfaces repeating. They're just multiplicities and unions. And it's only when you get to the dense that you realize that they're new minimal surfaces.
Yeah, so these minimal hypersurface might not be the ones that realize the volume spectrum,
Right.
the dense ones.
Right.
So it's possible that you have a dense set of minimal hypersurface, but still, when you compute the volume spectrum, you always get the minimal surface with multiplicities. Because we argue by contradiction, we don't know that. Of course, I would expect that multiplicities do not occur, and the minimal hypersurface that become dense and equidistributed are exactly the ones that realize the volume spectrum.
But that's still open.
Yeah, that's still open,
Okay.
yes.
Thank you.
That's fine, yeah.
So I'm curious, in connection maybe with computing the constant AN, I don't know whether this has any relevance or not. I'm just curious whether you have a vision of what the surfaces actually look like. Should I be imagining the triply periodic thing on some very small scale or some other?
So I would, my wild guess would be the following. I think they should resemble, so let's just do on the tree sphere, okay? I would expect them to resemble in some way zeros of polynomials where the degree is going to infinity. So I think we can imagine them as being zero sets of eigenfunctions, even if this is only circumstantial. So they should become, I think zeros of polynomials where the degree goes to infinity is a good example.
They're crossings and zeros, so that's not quite maybe some resolution of those?
I would expect them to become dense and equidistributed over all space, so to have like lots of necks everywhere.
Yeah, you have to stick in necks where the crossings of the
That's
zero
right, yeah.
sets would happen. Okay.
But very little is known about what these things should look like.